I'm hoping this is the most obvious video of the whole chapter for you, because my claim is that you pretty much know all of this already. But let's introduce it a little bit more formally, which is something this book doesn't do that often. So we're going to say that y naught, the vector y naught, is an equilibrium point. Oh, equilibrium. I know what that means. We'll say it's an equilibrium point for some differential equation written dy dt is some function of the vector y if f of y naught equals 0. Not surprising, right? We have some value, in this case it's a vector value, it's an equilibrium point if it makes the rate of change equal to 0. This is what we call the rate of change function. All right. And that's a very similar definition, which we'll include here, is that we're going to say that f, I want to get my notation right, f of y naught, oops, that's why I checked. Sorry, trying to get consistent. We're going to say the function, again, vector valued function, y of t equals y naught. So the function, the constant function that equals the equilibrium point, is what's known as an equilibrium solution. All right, so this definition kind of clarifies something that we glossed over a little bit. What's the difference between equilibrium point, equilibrium solution? Equilibrium point is the value. In this case, it's a vector value, whereas equilibrium solution is the function that's equal to that value. All right, solutions to differential equations, remember, are functions. Anyway, so let's get some practice over here, and I'm going to have you find the equilibrium, or equilibria maybe. Find the equilibrium points for the following system. dy dt equals 3x plus y divided by x minus y. Again, this is a fantastic time to pause the video. We don't really learn math by watching, most of us. We learn math by doing. So please pause the video, try to find these equilibrium points. So we know the equilibrium points are when the derivative is equal to 0. This is the derivative. So when is this equal to 0? Really, we're just doing more algebra. We just have to solve this system of equations. I can add these two systems together, or these two equations together, and we're going to get 4x equals 0. Oh, so x has to be equal to 0. If x has to be equal to 0, what does y have to be? That's it. There's only one equilibrium point, right? Our equilibrium point is the vector 0, 0. If we were asked the equilibrium solutions, we'd say the equilibrium solution is the function y of t equals 0, 0. This is a function, a vector valued function, which has two constant functions of 0, which is kind of weird to think about. You may not have had too much experience with vector valued functions, depending on what your math and physics history is. But that's all there is to it. And we can visualize this system. We can look at the direction field. We could look at the vector field. And so let's do so. So here I have both the vector field and the direction field for this system. And you can notice that they look pretty similar. Remember, what's the difference between a vector field and a direction field? Direction field says, I don't care about speed, I don't care about time. Direction field says, let's make all the vectors the same length. Whereas in the vector field, right, we can really see that kind of close to the equilibrium and kind of in this space, right, we're not moving very fast, which makes sense because our equilibrium 0, 0, when we're close to 0, 0, these vectors are pretty darn small. All right, so yeah, there's not much speed here. We can think of like flow of some kind of liquid, right? It's not very much speed here. And they seem to be getting like turned away from this equilibrium in a sense, right? And then the further we get away from that equilibrium point, we really start building up speed. So again, the vector field here is actually kind of nice. We can really see what's happening in terms of speed. Again, a lot of times we don't really like vector fields because they can be pretty hard to read because the vectors can do nut crazy stuff. Whereas direction fields are much nicer to show us like where things are going. But again, for this, I think the vector field's actually very, very nice. Okay. This is our vector field and our direction field. And you can see, yeah, there's only one equilibrium. It's at the origin, and it's going to be hard for things to get to the origin. In fact, it seems like they're getting turned away from it. We could also use numerical approximations, which again is covered in 2.5, which we're probably not going to go over ourselves. And we could plot some solutions. All right. And so it turns out that we actually can get like really close to this equilibrium. I don't know if we're actually going to approach it we might approach it directly, or whether we just get really close. You can see some different solutions. And we could plot some different solutions too, right? Like we could just follow the arrows. If we're here, we're going slow, and then we kind of speed up, and we go that way. Right? If we start up here, maybe we're starting over here, and we just go pretty fast over here, pretty quickly. You know, maybe we're over here, and we go pretty slow, and eventually we're going off over here pretty quickly. And you're going to see like a lot of very similar behaviors, kind of no matter where we start. Right? We can plot some solutions for different initial conditions. Right? No matter where your initial condition, you just follow the arrows to kind of see where you should go. And again, when we draw these little solutions, there's no real aspect of time. Here's another such solution getting kind of plotted. This is an approximation, right? They should really curve more than this, I believe. But this is just kind of showing what happens. And then again, you can also use a variation of Euler's method to get an idea of the solution itself. Over here we actually do finally have time incorporated. And you can see for some initial condition. So here the initial condition, right, is the x value is -1, or I don't know, -0.75, and the y initial is 3. Again, that corresponds to this point. You can see how x is slowly getting close to 0, and then it eventually shoots off. So we can really see the speed here. Y is getting closer to 0 as well, and it again also will eventually shoot off. That's pretty much it for this one. Let me know if you have any questions, and see you next time.